My name is Evan. I'm a professor at the University of Notre Dame. Tonight we are using an instrument on the Keck II telescope. So there are two Keck telescopes. There was one called Keck I and another one very creative called Keck II. Because why build one when you can build two for twice the price? They're nearly identical. They're mirror images of each other, but they have a completely different suite of instruments behind them. And the instrument we're using tonight is a spectrograph called the Keck Cosmic Web Imager. All right, everyone, what you're looking at is
Exposure complete.
you're looking at the control panel for the Keck Cosmic Web Imager. In particular, you're looking at on the bottom right, what you're looking at is where the telescope's pointed right now. And it might look like an eyeball, like you see like a pupil here. In fact, this is literally called a pupil. And this looks like the iris of an eyeball with a bunch of flecks in it. Those flecks are all stars. And in fact, they're stars that are in the globular cluster called Messier 15, M15.
The readout complete.
And the reason there's this black spot in the middle of this field is that this image here is an image just to see where we're pointed the telescope. That's the outside of it. But the inside of this black spot, all the light that would be here is being sent to the spectrograph. It's being sent to KCWI. And we don't want to throw away any of that light at all. So we're taking absolutely every bit of the light that would ordinarily be here, and we're sending it down a very complicated optical path to get a spectrum of all of those stars. So I'm not interested in pictures of stars. I'm interested in spectra of stars, because the idea of what we're doing tonight is to figure out what stars are made of. And the best way to figure out what a star is made of is to get a spectrum of it, to look at its absorption lines. And I might be able to show you an example of that a little later tonight. KCWI is an instrument that has what's called a dichroic filter. And what that means is it takes the light and it splits it into the blue light and the red light. So all of these stars that are behind this black spot are being sent down to the spectrograph, and we can see the blue light for the stars on one side of the spectrograph and the red light for the stars on the other side of the spectrograph. The reason we do that is the time on Keck is very precious. It actually costs $140,000 a night to operate the Keck telescope. And so we're literally counting photons, and every photon has a price to it. We want to make sure we count as many of those photons as possible. One of the most difficult things to do in optical engineering is to make sure you count every photon. You always throw some photons away. And it's best to design your spectrograph to not throw any of those photons away, or to throw as few of those photons away as possible. And so the way that these clever optical engineers have designed KCWI is a blue channel that's very sensitive to blue light at the expense of red light, and a red channel that's very sensitive to red light, but at the expense of blue light. So you send all of the blue light to the spectrograph that's good at blue, and you send all of the red light to the spectrograph that's good at red. This is called a double spectrograph. It's a very common way of using astronomical spectrographs. So on the top right is the control panel for the blue side of KCWI, and on the bottom left is the control panel for the red side of KCWI. We have exposure times. You can see the exposure time on the blue side is 540 seconds. 540 seconds is 9 minutes. The exposure time on the red side is 150 seconds, which is 2.5 minutes. You can see we have 2.5 minutes times 3 exposures that we're doing right now. And on the blue side, we have 9 minutes, 540 seconds times just 1 exposure. And maybe a little bit later, we'll get into why we have a different number of exposures on the red and the blue. But what the exposure looks like, if you direct your attention to the top right of your screen, you see this kind of blue thing that's coming into view. Exposures look like rows. I'm going to zoom in here so you can see a little better. Even better. And so, okay, so you see these rows, these kind of horizontal rows with the dark lines in between them. What you're looking at is a spectrum of a particular spot on the sky. And this row next to it is a spectrum of a spot in the sky right next to this spot. And this one is a spot right next to this spot. So what KCWI does is take spectra of different slices of the sky. In fact, it's called an image slicer. It takes an image of the sky, slices it up very finely, and takes a spectrum of each one of those slices. And then when we process this light, this image through the data analysis or the image analysis software, what it does is gives us something called a data cube. It's a picture of the sky. In fact, on the left, what you're looking at is a data cube. It's on the top left of your screen. This is a picture of the sky. So these are various stars and nebula that are in the sky. But for every one of the pixels in this image, I could click on it and show you what the spectrum looks like. And so right here, you're looking at the spectrum of a particular star in the globular cluster M15. A spectrum is a chart of how much light is coming out at each color or each wavelength. And so all the light has been split into its component wavelengths. And you can see that some wavelengths are missing light. There's this chunk taken out of the spectrum right here. And that chunk taken out of the spectrum is an absorption line. It's due to a certain element. Maybe this is actually probably the element iron that's absorbing the light at this wavelength. The fact that this absorption line is here tells me that this star has iron in it. And in fact, it probably has a fair amount of iron in it because this absorption line is pretty strong. There's other absorption lines here that are due to different elements. Here's another absorption line. Here's another one. Here's another one. This absorption line is actually due to the element hydrogen. So this is a big, strong line of hydrogen because a lot of stars have a lot of hydrogen in them. But then all these other absorption lines could be, I mean, if I looked it up in a data catalog, I could tell you which elements these are.
Exposure.
It might be iron, it might be calcium, it might be silicon. These stars have all of those elements in them.
Excuse me, Evan.
Okay, one moment. I'm talking to my colleagues because they're about to change targets. Juyun, yeah, the PPA should be 75.
CCD readout.
Yes,
complete.
exposure times as M15. Thank you. Tamika, I'm sorry, please.
No worries at all. Thank you so much. We are not able to see which screen you're talking about.
CCD readout complete.
Oh, no. Okay. Okay. Let me try that again. So can you see a whole bunch of complicated stuff, 4 different panels?
Yes, we see the 4 panels.
Okay. And so was it my cursor you weren't able to see?
Yes, I believe so. We had a comment that they could see all 4 of the screens, but couldn't tell which screen, all the detailed analysis you were saying to us, which screen that pertained to.
Got it. Okay. One moment, shout of the scientists, observers. I'm lining the star field right now. Okay, y'all. I am here. I can help look at this guider image and see if we're aligned in the right spot. You know what? I would like to try pointing 2 instead of pointing 1. Actually, well, hold on 1 second. Hold on. Yeah, no, I'm not a fan of that. Actually, no. Okay, no, I see it now. Those 3 stars there. Could we so move object up in guider coordinates? So that way it's up. So I want to move it right then, because I want to get this star here a little bit closer to the center of the frame. No, I can see it. Those are the three stars I want. 1, 2, 3. So if I move this to the right. Okay. Okay, sorry. Probably, I'm gonna say 3. I don't want to move it too much or else the one on the left is gonna fall out. Oh yeah, I did move it the wrong way. I did move it the wrong way. Thank you, Tony. So I'm gonna move it to the left by 6 arc seconds then. No? Yeah, that was this star here, this star here, and this star here. I want all 3 of them. Oh, okay. Sorry, that was my misunderstanding. It's the magenta box. Okay, in that case, okay, sorry, that was my misunderstanding. And so, okay, so what I should do then is, okay, so I should probably move this 8 to the right so I can get at least 2 of the stars. Okay, that looks good. That looks good. Thank you. Okay, so when we come back from the sky, we're going to rotate 90 degrees. We want to make sure that both of those stars are still in after we rotate. Both of these stars, this one and this one. This one and the bright one. Both stars should still be in the field after we rotate 90 degrees. Absolutely. Yeah. Okay. Good idea. All right. Thank you. Hello, everyone. Let me explain what just happened here. We have moved to a different globular cluster. In fact, you can see, if you look at the bottom right of your screen, there's, again, that eye-looking thing with the pupil and the iris. Now there's a different pattern of flecks of stars. Every one of those points of light is a star in a globular cluster. This globular cluster is called M30. What we're trying to do is observe a very specific patch of this cluster. In fact, that very specific patch is zoomed in on the top left of your screen. And what we were doing is we were centering, oops, so my colleagues are moving on to other things with the observing, but previously what we were doing is trying to center 2 of the particular stars that I had picked out before on the field that we were going to observe with the spectrograph. So remember, the bottom right field is just a picture of the sky, but what we're really trying to do is take spectra of particular parts of the sky. And so that guider image on the top left that we were discussing, you might have heard me say we're moving left, moving right. We're trying to center the spectrograph aperture on a particular patch of sky that includes the 2 stars that I was interested in. Now, the reason I'm interested in these stars is not because I don't know what they're made of. And in fact, I know exactly what these stars are made of because I actually have a really, really good spectrum of each of those stars from a different Keck instrument called HiRes, a high resolution Echelle spectrograph. And this is the first time I'm using KCWI to do this kind of work of measuring the compositions of stars. And so I really want to be able to prove that when I measure the abundances of stars or the compositions of stars with KCWI, I get the same answer as that very trusted spectrograph high res. And so I'm intentionally re-observing stars with KCWI that I have already observed with a different spectrograph. Now, at the end of the night, like hours from now, hours from now, I'm going to be observing a totally different cluster that's much farther away.
CCD readout
It's in a
complete.
different galaxy. In fact, it's not even in our Milky Way galaxy. This globular cluster that we're observing now, M30, and the one we observed before, M15, both of those are star clusters that are in our own galaxy. But at the end of the night, I'm going to be observing a distant star cluster that is not even in our galaxy. It's a completely different galaxy called the Fornax Dwarf Galaxy. And I have no idea what those stars are made of, but KCWI is going to tell us. And I'm going to have confidence that I believe my measurements because I'm going to prove that I get the same results for M15 and M30. This clusters where I already know their compositions. So I'm kind of making a ladder of confidence. I know what these stars are made of. KCWI gives me the right answer. Therefore, I can now point KCWI at stars where I don't know what they're made of, and I can be confident I have the right answer. So after we finish observing this cluster, there's going to be a couple of hours, maybe an hour and a half, before the Fornax Dwarf Galaxy is visible. One moment, my colleague's talking to me. Thank goodness. Okay, thank goodness. Yeah, okay, that's a beautiful spectrum. Okay, okay. Now I'm seeing electrons that are close to 60,000 there. Does that mean it's close to saturation? Oh no, because you're averaging, oh, you're adding up a bunch of pixels. Okay, yeah. I got worried for a second there. Okay, good. That's good to know. Oh, those are beautiful spectra. Can you, oh, look at that. That is such a gorgeous spectrum. Yeah. Okay, so for the side of the scientist people, my colleague Zhu Yun is showing us an image of the sky that we just took with the spectrograph. And when she moves her cursor over these stars, each one of those specks of light is an individual star. And when she moves her cursor over the star, we get a spectrum of that star. That is a really, really nice looking spectrum.
Complete.
You can see a whole bunch of absorption lines, and each one of them corresponds to an element in the star's atmosphere. Ji-Yun, thank you very much. Say again? Oh, okay. Thank you, Ji-Yun.
CCD readout complete.
Okay, so I was saying that's a really beautiful spectrum of that star, and it's because it's just so textbook looking. It's got a very well-defined top. There's no stuff poking above that continuum at the top, and then there's a whole bunch of absorption lines dropping down from the bottom of that continuum. That's exactly what a stellar spectrum looks like in a textbook, and we have an example of that here with KCWI. I'm going to point out 3 absorption lines in particular. It's these 3 absorption lines right here, if you can see where my cursor is. These 3 absorption lines are due to the element magnesium. In fact, this is called the magnesium triplet because there's 1, 2, 3 absorption lines. They're really, really close together. This is 1, 2, 3 absorption lines. And they're really, really excellent for determining how much magnesium is in this star. you can see that they're by far not the only absorption lines in the spectrum. Every one of these absorption lines is good at telling us the abundance, about the composition or the concentration in that atmosphere of the amount of each one of the elements of the periodic table. And what we're actually sensitive to is concentration. So you might be familiar with the concept of parts per million or parts per billion. You might often think of like carbon dioxide in the atmosphere. How many parts per million of carbon dioxide do we have in the atmosphere? Well, for stars, the relevant numbers are actually parts per billion. And so, for example, the sun has about 100 parts per billion of iron atoms in it. This particular star is a lot less iron rich than the sun. In fact, it's a lot less rich in almost every element except for hydrogen than the sun. And so here we're talking more like parts per billion rather than parts per 100 parts per billion. And that's also true for magnesium. Magnesium is also about a concentration of 1 part per billion in this star. That in itself is kind of amazing if you think about it. Like, there's a lot of elements in the periodic table, but they're really tiny, tiny fractions of what make up stars. The vast, vast majority of stars is just boring old hydrogen. Hydrogen and helium
complete.
and not much else. In fact, if you add up all of the elements heavier than helium in the sun, it only makes up about 2% of the sun. So one of the ironic things we have to do when we're observing is once we've finished observing a star field, we actually have to observe blank sky. And the reason is that the Earth's atmosphere glows. It glows brightly. In fact, it doesn't glow bright enough for us to really see it with our naked eye. If you go to a dark site, like the summit of Mauna Kea in the middle of the night, which is where the Keck telescope is, and you look up, you're just going to see blackness. But if you're the Keck telescope, you don't see blackness. You actually see the sky is glowing. And whenever we look at the stars, we have to look through the Earth's atmosphere. That means we have to look through the glowing sky. So whenever we get a spectrum of one of these stars, we don't just get a spectrum of the star. We get a spectrum of the star plus the spectrum of the Earth's atmosphere. And even at night, the Earth's atmosphere is glowing. And it's glowing not just in white light, it's glowing in the whole rainbow of colors. And so what we do is we observe fields that are off sky, meaning where we move the telescope to a blank field that doesn't have very many stars in it. We take a spectrum of that blank field, which should be just pure Earth atmosphere. And then we subtract that from the original pointing. So we originally had star plus Earth, and then we subtract Earth. We're just left with star now. And so that is one of the more nuanced things about observing with a spectrograph is that you always want to do sky subtraction, meaning subtract off the light of the Earth's atmosphere. I mean, I'm a human being, so I like living on the Earth's atmosphere, but as an astronomer, gosh, I hate the atmosphere. I'm wondering if anyone has any questions about what's happening here. I imagine this is all very
Do the satellites affect your view of the remote galaxies? Do you ever have them passing over?
That's a good question. Only very rarely. Satellite passes usually affect imaging, not spectroscopy. And the reason is that the area of sky that we are taking a spectrum of right now is really, really, really tiny. And so, for example, if you hold your thumb up at arm's length, that is a few degrees on the sky. We are observing about 1/10,000th of a degree on the sky right now. And so it's a really, really, really tiny section of the sky. And the chances that a satellite are going to pass through that is negligible. On the other hand, there are lots of imagers that image tens of degrees on the sky simultaneously. And the chances that a satellite is going to pass through a circle that's like 20 degrees wide is pretty good. And so it is true that things like Starlink are really a problem for
Exposure
imaging experiments
complete.
on telescopes with wide fields of imaging, but for very narrow field spectroscopy like we're doing today, it's not a problem. But there's a whole industry of satellite mitigation for astronomers.
Yeah, it'd be interesting to find out what they're doing with that.
Say again?
I said it'd be interesting to understand the technology to delete the satellites.
Indeed, yeah. Most of it is image processing,
CCD readout
especially
complete.
if you know when the satellite's going to pass. It's called the ephemeris of the satellite. If you know the time and trajectory of the satellite, it's easy to make a model of what that pass looks like and then remove it digitally. There's also a fair amount of just lobbying, lobbying Elon Musk. Please don't send more satellites into space. Of course, that doesn't work, but
no, I think he's got 20,000 more planned.
yeah. And there are some astronomers who are deeply concerned about it. The astronomers who are really concerned about it are actually radio astronomers, because satellites are very noisy in the radio bands. And unlike the visible light, where they're just specks of light, in the radio bands, they just are like giant blasts of radio energy that go in all directions, not just a single point. Do we have other questions?
I don't see any other questions in the chat right now, Evan.
All right. So I am actually fairly new at using this spectrograph. I am one of the world's experts at a different spectrograph on Keck called DEIMOS, the Deep Imaging Multi-Object Spectrograph. But this KCWI is a fairly new experience for me. This is only the second or third time that I've used KCWI. And the last time I used it, it only had a blue side. You might remember I said earlier that there's this thing called a dichroic that splits the light into blue light and red light. Dichroic, if you break that down, di is two and chroic means the colors, two colors. So you split the light into the two different colors, blue and red. But the red channel of KCWI did not exist until this past summer, because they built the blue side first. And then after that was successful, they raised enough money to build the red side of it and then finished building it. It took maybe 6 or 7 years to build the red side of this spectrograph. So the last time I used this, we didn't have the advantage of getting such a large spectral range. And so you're looking at the spectrum that Juyun is playing with on the top. By the way, Juyun's a PhD student. She's a PhD student at Caltech. And the spectrum she's playing with in the top left is really just the blue side. But there's another spectrum also on the red side that she hasn't finished analyzing yet. So there's twice as much data that we're getting now than we got, say, if we used this spectrograph last year. And it's because of this brand new fancy red side to the instrument. And so that's been very exciting to have this capability. To give you a sense of scale, these instruments cost in the order of 10 or $20 million. And so it's a pretty cutting edge technology. And so it's all very specialized. Most of that money goes into paying labor to people. And the reason I'm talking about this is because I'm currently trying to upgrade the DEIMOS spectrograph. I currently am upgrading the DEIMOS spectrograph, but most of my job is, not most, but a good chunk of my job is raising money to do so. Don't worry, I'm not about to give a sales pitch. Understanding the raw data for KCWI is one of the more complicated things in astronomy, in the Keck instrumentation. Some of the spectrographs, you just look at the raw data and you can sort of tell what it is. But even when I look at like for example, the bottom left, that's the raw image from the red side. I sort of know what's going on, but it's hard for me to picture how to go from this to an image like you see in the top left. But on the bottom left, that's the raw image that comes out of the instrument. And the detector that's used is quite similar to like the detector in your phone, for example. The device in your phone is called CMOS. The device inside of KCWI is called CCD, a charge coupled device. They're slightly different technology, but they're in essence, they're both just silicon. And so what you essentially have is a digital camera. That's what KCWI is. It's a digital camera. And the detector that we have here, the main difference between it and your phone is that the detector in KCWI is very, very sensitive to light. When you're taking images with your phone, you're usually taking them with either artificial light or with sunlight, and you've not starved for light. You can afford to throw away a lot of photons. But with the Keck telescope, we're very intentionally trying to look at some of the faintest things in the universe. And so we are starved for photons. And so the technology that's different mainly goes into making sure that we're counting as many photons as we possibly can. All that's to say is that KCWI at its essence is really just two digital cameras. One for the red light, and one for the blue light. Now you might notice that there's a whole bunch of these streaks in the bottom left image, and they're mostly present in the bottom left or right. And you're going to rotate by 90 degrees, is that right? Thank you. I do want, yes.
CCD readout complete.
Is it okay? Okay, great. Oh.
CCD readout complete.
Okay, everyone. So what we've done, we're going back to the same field we were observing before. We just finished observing our blank sky, so we can get our image of the Earth's atmosphere. And now we're going back to the same field we observed before, way in the outskirts of this globular cluster called M30. Okay. Yeah, we're going to have to move that up. Up in the direction of the down. Yes, sorry. I'm trying to move the box up, but I really should be moving the stars down. A little more, yeah. A little more, please. A little more, please. Same amount. And that should be good. I think you have to change the stretch. Okay, that's good. Okay, Tony, let's send it to. Excellent. Thank y'all. So what y'all can't see on Shadow the Scientist is that I'm actually on another Zoom. I didn't know how to do it on my computer, so I'm actually on my cell phone. I'm talking to a whole lot of people. I'm talking to actually 5 of my PhD students, 1 telescope operator, and 1 support astronomer. The support astronomer is in Hawaii. She is at the observatory. She knows very well how to use this instrument. I've only used, like I mentioned, this is only the second time I've used this instrument. So it's not like I just show up here and I know what I'm doing. I need someone to help me, and that's what her job is. They also don't let the dumb astronomers like us drive the telescope. And so the telescope operator is the one who is paid and certified to do that. And so you might have heard me just say, Tony, we're good to go. What that means, I'm talking to the telescope operator, whose name is Tony, is sitting right next to the telescope. He's the one who actually repositions the telescope. The Keck telescope is a 10-meter mirror. It's a lot of metal moving around. And so you probably want someone who's certified to drive it to do so. And when I say drive it, what I mean is point it at a certain spot in the sky. In order to point this telescope, it's not just like, I'm just going to move it with my hands. It weighs many, many, many tons. So you're moving all of this many tons of metal, rotating it, tracking the sky. The dome is moving to make sure that the open aperture that's looking at the sky is also aligned with where the telescope is pointing. So there's a lot of stuff that's going on that requires someone whose dedicated job it is to do that, and that's Tony. So they don't let me point the telescope, only the telescope operator can do that. The person I keep talking to is Zhu Yun. She's a fourth-year PhD student at Caltech. Oh, sorry, now she's a fifth-year PhD student at Caltech. I also have another fifth-year student online, and I also have 3 second-year students online. And they're all in residence at Notre Dame. But they're all here because they want to get some of this data for their dissertations, or in the case of Zhu Yun, this is not data that's going to help her dissertation, but she has actually used KCWI a lot more than me. And so she's been very helpful in making sure I don't do dumb things, which I've already done a few times tonight.
Exposure complete.
You might be able to hear the signal that the exposures are complete. It can be slightly annoying, but it's good when you're in the middle of the night and sleepy and haven't you're kind of sleep deprived and you're thinking about bed. It can kind of jolt you awake. It's like, oh, I should be doing something now. Remember what I said? It costs $140,000 a night to operate the Keck telescope. So even zoning out for a minute is quite costly. So you want all the reminders that you can have to make sure it reminds you to do your job.
Complete.
And to do it on time without wasting precious photons. Do we have more questions? Up in the chat. Let me have a look.
So when you focused in on it started, how many nanometers did you move did you actually move the telescope, or did you just change the focus, or how did you hone in on that? And how many nanometers did you move it?
Nanometers, that's a good question. Yeah. So when we moved the telescope, we moved it in angle. And the angle that we moved it by was about 3 arc seconds. So I mentioned a degree on the sky. So the full moon is half a degree on the sky. Half a degree is 30 arc minutes. There's 60 arc minutes in a degree, and there's 60 arc seconds in an arc minute. So an arc second is 1/3600th of a degree, and we moved it by 3 arc seconds. It's a very, very small amount. It would be imperceptible if you were just looking at the telescope. But the edge of the mirror probably moved by a few millimeters, not nanometers. It's probably a bigger move than that. Okay. But if you're looking at like how much the telescope edge moved relative to its center, it's probably a few millimeters.
I see. Much larger.
That's right, yeah. Now, the Keck primary mirror is not a single piece of glass. It's actually 36 pieces of glass, 36 hexagons that are tessellated. And because the telescope's moving like this over the course of the night, gravity is pulling on those 36 segments differently, and they get a little bit out of whack. And so there are sensors that are monitoring the different levels of how the mirrors are aligned, how the adjacent mirrors are aligned with respect to each other. That precision is on the order of nanometers. That is really, 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 really precise.
Yeah, that's what I read. I think twice a second it adjusts those.
Yes, yes, it is constantly updating those positions based on real-time measurements from the sensors that are between each of the mirrors. The primary mirror is only one of 3 mirrors that is in the main telescope optical path. The primary mirror reflects light into a secondary mirror. The
Exposure.
secondary mirror is, I don't remember exactly how many meters above the primary, I think about 8 meters above the primary. And when we focus the telescope, what we're doing, we're changing the distance between the primary and the secondary mirrors. The amount at which we change that focus is on the order of microns. It's really, really small, 1/1,000,000th of a meter.
CCD readout complete.
So this is the last exposure we're going to do for these globular clusters until the Fornax dwarf galaxy becomes visible. Okay, so yeah, let's turn it over to Evan. And we need to remember to change the configuration, of course. But we can do that while we're slowing. Which one are you starting with, Evan? Okay, want me to highlight it for you? Okay, okay. Sorry about that, y'all. So I was saying that the Fornax dwarf galaxy is still rising in the sky. It just came above the horizon. It's not yet high enough for us to observe with the telescope. We don't want to point at things that are right at the horizon because there's a lot of Earth's atmosphere in the way, and they're hazy and they're faint. I would like to start at the original time on the run plan on Fornax. Right to probably going to have about 1:40. Maybe an hour, maybe 1:35. Yeah, sorry, we kind of ate into your time a little bit. My pleasure. So we don't want to point at things that are close to the horizon because there's a lot of Earth's atmosphere in the way. The Earth's atmosphere is hazy. It's got dust. It's got things that obscure the light, and it's not very efficient to point at things that are low in the sky. So we want to wait for those globular clusters in the Fornax dwarf galaxy to rise and get higher and higher. And while we're waiting for that, we're not just going to sit here and do nothing because, again, $140,000 a night. And so my PhD student, who also happens to be named Evan, is going to observe stuff for his PhD thesis, which involves quasars. Quasars are fantastically more distant than anything that we've observed so far tonight, and they're and you should change your configuration now, Evan.
Readout complete.
So the Fornax dwarf galaxy that we're going to be observing at the end of the night tonight is about 180,000 light years away. Actually, no, even more than that, 260,000 years away. They put all sorts of weird noises as we're moving the instrument around just to make sure you're paying attention. But the quasars that Evan Nunez, not Evan me, that Evan Nunez, my PhD student, is about to observe are more like billions of light years away. And this is so his PhD thesis is on a completely different topic. It's not what are stars made of. He's actually trying to find galaxies that are only visible because there's a background light source illuminating them. So he actually is not interested in the science of quasars. He's just using the quasar as a background light source. A quasar is the active center of a really, really star-forming galaxy. So it's got a supermassive black hole. This supermassive black hole has a bunch of stuff accreting onto it, and it's very bright, it's very hot. And that's very exciting science, but he doesn't care about any of that. All he wants is just this background light source to illuminate the galaxies that are in the foreground. So this quasar that he's looking at is billions of light years away, and the foreground galaxies that he's looking at are just slightly less than billions of light years away. So the quasar might be 3 billion light years away, and the foreground galaxy that he's looking at is 2 billion light years away. What his thesis is on finding those galaxies and then figuring out what the gas around those galaxies is doing. Now, we're going to see the quasar come into the field in a few minutes from now, and despite the fact that I gave it a very exciting introduction, like a supermassive black hole, it's creating matter and very hot and glowing, very bright, it's just going to look like a star. It's not going to look like much else other than just a speck of light, which is what a star is. Now, the spectrum will look very different from what stellar spectrum looks like. It'll look, why is it? Okay, there's more weird noises to make sure we're paying attention. So we're about to see the field with the quasar in it. If you look in the top left, Evan is taking a picture of where the field with the quasar is. It's not going to look super exciting. Again, it's just going to look like a speck of light, and there it is. So that little speck of light is a quasar that is about 3 billion light years away, if not further. Evan's trying to get it centered up in the middle of that field.
Is the spectra from that quasar not detectable?
Hold on one minute. My ear is being talked into. Sorry, go ahead, Scott.
The absorption lines from the quasar, are they not observable?
Oh, they absolutely are observable. Yeah. So once we get a spectrum we're about to take a spectrum of this quasar, and once we do, we'll be able to see the absorption lines in it.
And how do you detect the absorption lines from the quasar versus the galaxies and the gas in front of it?
Oh, that's a fantastic question. It turns out that the quasar only has absorption line. So quasar has a lot of hydrogen gas in it, and there's a very strong mission line of hydrogen gas at 1,216 nanometers. 121.6 nanometers. It's called the Lyman alpha transition of hydrogen. And to the blue side of that, to the shorter wavelength side of that, there's a bunch of absorption lines in the quasar. But to the red side of it, there's not. And so the spectrum of the quasar is free of absorption lines to the red of that Lyman alpha. And so if we see absorption lines, we know they're not from the quasar. They have to be from something in front of the quasar. And so it's strictly the wavelength of the light we're looking at that tells us whether the absorption line is in the quasar or in something in the foreground of that quasar. The reason we see those absorption lines is that there's gas in front of the quasar, and it's absorbing light out of the quasar line of sight, but at very preferential wavelengths. And those wavelengths are because the foreground galaxy has hydrogen and it has other elements in it as well.
Evan, we did have another question in the chat, but I think maybe there was just a bit of clarification needed on quasars and black holes. So the question is, how do black holes emit quasars if they break causality within the event horizon? But I think, as you were saying, quasars are galaxies with active black holes.
That is correct. The quasar itself is not a black hole. There's a black hole at the center of the galaxy, and material is falling onto the black hole. And as it does so, it heats up quite a lot. And that material is glowing. So we're seeing the glowing material as it falls onto the black hole, but we're not seeing the black hole itself. Good question. You're quite right. We wouldn't be able to see the black hole itself emit light. The thing that's emitting light is the gas that's heating up as it falls onto the quasar.
Thank you. And then we have a follow-up question. During absorption, is there then re-emission at a different wavelength?
Oh, that's a fantastic question. Why, yes, there is. The reason that we have absorption lines is that there are atoms in the gas. Atoms, the definition of an atom is you've got a nucleus and you've got electrons bound to that nucleus. And the electrons are orbiting that nucleus, but they can orbit with different energies. So you might have an electron orbiting very close to the nucleus with low energy, or you might have that same electron orbit far from the nucleus with a higher energy level. And so what happens with an absorption line is that a photon gets absorbed by the electron, and that electron jumps up to a different energy level. And so the presence of absorption lines indicates electrons moving back and forth between energy levels and atoms. Now, you might think that once the electron jumps up to an energy level, it can fall back down to the same energy level and then emit a photon of the same wavelength, which can happen, but it can also cascade down to different energy levels along the way and emit those photons elsewhere. That's exactly what happens. And so as the photons absorb energy and get, as the electrons absorb energy from the photons, cause the absorption lines, they'll re-emit that energy in other wavelengths.
CCD readout complete.
You're looking at the bottom left, Evan Nunez, not Evan me, Evan Nunez is playing with looking at the raw spectrum on the red side, and you might see a whole complicated pattern of vertical lines. Each one of those vertical lines is actually not part of the quasar. The quasar is the horizontal lines. You see the bright streak running from left to right. That's the quasar that Evan is interested in. The vertical lines are the emission lines of the Earth's atmosphere. So I mentioned earlier that the Earth's atmosphere is glowing. It's the bane of my existence as an astronomer. I don't want to look at the Earth's atmosphere. I want to look at the stars behind the Earth's atmosphere. But it's glowing not uniformly at all wavelengths. It's glowing very brightly at some wavelengths and not very brightly at all at other wavelengths. That's because the Earth's atmosphere has a bunch of molecules in it. The molecule that you're looking at there is called hydroxide, OH. It's actually an ion, OH minus. If you remember your high school chemistry, you might remember that hydroxide is the ion that causes bases to be basic, to have a high pH value. Well, that ion exists in abundance in the very upper levels of the Earth's atmosphere, and it glows at very discrete and regular wavelengths, and that causes that telltale pattern in the spectrum that we're looking at. The reason we observe blank sky fields is to get a template of all of that emission and then be able to subtract it out from our science spectra where we're observing the quasars or the stars or the galaxies. But the thing that Evan is most interested in is that quasar. In fact, what Evan has done is get a very rough spectrum of the quasar. And what you're looking at, the spectrum is the graph called projection, the one that I'm about to make bigger here. It's got a green outline. I'm going to expand this window. If it lets me. And you can see all of those emission lines, the upward spikes. That's all the junk from the Earth's atmosphere, that pesky atmosphere that we unfortunately have to breathe. But there's also things that are pointing down. And notably right here, there's absorption lines that are pointed down in the spectrum. And so that is one of the possible foreground galaxies that Evan is interested in, Evan Nunez. is interested in, because that's chunks of light missing from the quasar spectrum. And it's not because the quasar is missing those chunks of light, it's because there's foreground features, there's foreground gas from other galaxies that are absorbing those wavelengths of light out of the quasar spectrum.
Good question. The emission lines from the atmosphere, how long do they stay static in that pattern? Do they change over time?
The wavelengths themselves are very
Exposure
stable.
complete.
So they will not change in wavelength. So the left-right positioning of the absorption lines, of the emission lines is not going to change. However, the relative intensities will change a fair bit over the course of the night. There's in fact a 2-minute rule. They changed on roughly 2-minute timescales, and also over an angular scale of 2 arc minutes on the sky. So if we were to move the telescope by 2 arc minutes, which is 1/30th of a degree,
The readout
we might see
complete.
different relative intensities of those emission lines. That's why we take the off-field sky to see what the sky looks like right now. We can use that as a template to subtract the skylight from the target spectrum.
And that template's good for 2 minutes?
Well, it depends on how precise you want to be. We don't have to be super precise. And so when we take the off-field sky, we observe the target for maybe 15 minutes, then off-field sky for 15 minutes, then go back to the target for another 15 minutes. But if you want to be really, really, really precise with your Earth sky subtraction, then yeah, you would want to observe 2 minutes on target, 2 minutes on sky, 2 minutes on target, ad nauseum for the whole night.
No.
My particular science is not that sensitive to this exact sky subtraction, so I don't bother with being that precise. But there are some people who observe really, really faint galaxies who have to do that. Otherwise, the signal of their galaxies would be washed out in just the sky noise. That's real tedious observing. So you might notice that, point out here, if you can see my cursor, on the bottom left, you might be able to see my cursor. There's one row, one horizontal line here. There's another horizontal line here. There's another horizontal line here. There's a fainter one here. What you're looking at is, if you imagine the quasar is just a speck of light on the sky. So if you follow my cursor to the top left window here, there's a speck of light on the sky. But what KCWI does is it takes that image of the quasar and slices it. So there's a slice here, there's a slice here, there's a slice here, there's a slice here. So we're taking these horizontal slices through the quasar, and we're getting a spectrum of every one of those slices. In the end, we can combine all of those slices together to make a single image of the sky, where we're able to get a spectrum of every pixel on that image. This is called the integral field spectrograph. It's one of the things that makes KCWI very special. Most imagers, you just get a picture of the sky. You don't get a spectrum of every pixel. You just get a single white light image of the sky. Most spectrographs, you get a spectrum of a single point on the sky, but not a spectrum of every pixel in an image. An integral field spectrograph is the best of both worlds. You can take a picture of the sky, but also get a spectrum of every single pixel in that image. Now, that doesn't come for free. And one of the major disadvantages of integral field spectrographs is that they can only image a very, very small chunk of sky. So in this case, the field of view of KCWI is only 16 arc seconds. And remember, an arc second is 1/60th of an arc minute, which is 1/60th of a degree on the sky. So it's a really, really small chunk of sky. It'd be like one crater on the surface of the moon. Actually a pretty close analogy. The field of view of KCWI is about the same
Exposure
size on the sky
complete.
as one crater on the surface of the moon. Actually, one small crater on the surface of the moon.
CCD readout complete.
And one thing you might notice in the red image, the one on the bottom left, the one that Evan is playing with right now, is there's a lot of streaks and lines that are running through it, just kind of haphazardly and randomly. Those are what we call cosmic rays. So the Earth's atmosphere is full of particles like electrons and muons and tau, all of these elementary particles that are just flying around. A lot of these elementary particles come from really, really distant things like quasars that made these very high energy particles billions of years ago. They've been streaming through the universe. They struck the top of the Earth's atmosphere and they caused this cascade of particles to come down.
Exposure complete.
Now, CCDs or charge coupled devices are really, really good at detecting photons. They're also really, really good at detecting these cosmic rays. The red detector is very thick. It's 500 microns thick. That doesn't sound very thick, but it's pretty thick for a silicon device. Whereas the blue detector on KCWI is pretty thin. It's only tens of microns thick. Because the red detector is so thick, it's got a very high cross section for detecting these particles. And so it's a pretty efficient detector of cosmic rays, which is annoying because we don't want to detect the cosmic rays. We want to detect the photons. About half of cosmic rays actually aren't cosmic at all. They just come from the radioactive decay of stuff in the Earth. So you might know that if you have a granite countertop at home, it's radioactive because it's been contaminated with very, very small amounts of things like uranium, which is radioactive.
Complete.
And when I say radioactive, what I mean is it's spitting out electrons. Electrons are coming out of your granite countertop, which is why you might want to have things like radiation mitigation if you have a granite countertop. But just the rock and the Earth is also naturally radioactive, and it's radioactive at such a low level it's not going to harm you, but these detectors can see it and can actually see the electrons that are coming out of that radioactive rock. And so one thing that we do to mitigate the effect of those cosmic rays and the radioactive rock is to take multiple exposures with the red camera. Because what we can do is we can take medians. We can say if the cosmic ray is here in this exposure, but not in this exposure, we can just get rid of it. So we can do image processing things where we want to only keep the photons that are there across multiple exposures and throw away the photons that are transient, the ones that appear in one exposure, but not in the other exposure. So a lot of this astronomy business is really just like basic image processing. I don't want to say we Photoshop the images, but we are making educated guesses about which photons are real and which ones are not. Your plan is to do one more. Go ahead. Your plan is to do one more blue exposure after this one? Okay. Okay, so you're going to do a full hour on this one. Okay, that sounds good. I'm having a small negotiation with Evan Nunez about how much time he gets to observe his quasars before I get to move to my Fornax dwarf galaxy target.
So Evan, that quasar is about 20 pixels or so.
Exposure complete.
The quasar is about 20 pixels.
Is that correct?
It depends. So on the guider image, which you see in the top left of the screen, the pixel size is a lot different than the pixel size in the spectrograph. So you're, excuse me, you're correct that in the guider it's about 20 pixels, but in KCWI it's many more than that because pixels are smaller in KCWI.
CCD readout complete.
The guider looks at a much larger field of view than the spectrograph does. And so the detector sizes are not that different from each other. So if you're looking at a wider area of sky, it must mean that each pixel is looking at a larger amount of sky. So the night lasts from sunset in Hawaii to sunrise in Hawaii. So I'm here on East Coast time in South Bend, Indiana, which means I have to stay up till sunrise in Hawaii, which is about 5 hours after sunrise in Indiana. So it's kind of brutal observing from the East Coast of the US if we're observing from Hawaii. The weather tonight is okay. So the weather telescopes is a combination of a whole bunch of factors. First of all, we want it to be clear. We want there to be no clouds because clouds would obscure the sky. Of course, we don't want there to be any precipitation. We also can't even have high humidity because if the humidity is too high, then water will condense on the telescope, which is really bad. So another reason the telescope operator is there is to ensure the safety of the telescope. And that's a complex job, including making sure that the dew point doesn't get low enough that, the dew point doesn't get low enough that water will start to condense on the surface of the mirror. If it does, it would damage the coating of the mirror and it would be expensive and timely to recoat the mirror. Another thing is that we don't want the wind to be too strong because the wind can buffet the telescope and cause the image quality to suffer. But then one of the most common ways that the weather isn't very good is simply that the air is turbulent. The jargon that astronomers use is called seeing, S-E-E-I-N-G, seeing, like I'm seeing you with my eyes. If the seeing is poor, it means that the sky is very turbulent and the images look very blurry. If the seeing is very good, then the images look very sharp and crystal clear. So tonight we have great weather except for the seeing. The seeing is measured in arc seconds. It's how wide does a star image look like on the sky. Stars are so far away that they are just specks. They're point sources. We cannot resolve the disk of stars. There's only a couple of stars in the sky that we can do that, including the sun. But every other star in the sky, the vast billions, trillions of stars in the sky, they're just specks. But they don't appear as specks on our detector because the Earth's atmosphere takes that speck and blurs it out. And the angle of how much it's blurred out on the sky, measured in arc seconds, is the measure of seeing. Typically on Mauna Kea, the mountain that the Keck telescope is on, good seeing is considered 0.7 arc seconds or less. We want the image to be as small and sharp as possible. Tonight it's 1.1 arc seconds, so it's not super great. There are things you can do about the scene. There is a whole technology called adaptive optics, which constantly measures the turbulence in the atmosphere, and it employs very rapidly moving optics to correct for that turbulence. It's not altering anything about the atmosphere, but it's altering the way the light goes through the instrument. What's happening is the light is arriving at slightly different times because of the turbulence. So the mirror in this adaptive optics system actually deforms to catch the light earlier or later. So this kind of misshapen wavefront hits a mirror that has the same shape, and then it gets flattened out. It's a really cool technology.
Exposure
future.
complete.
But this particular instrument does not use adaptive optics. Adaptive optics is expensive in terms of photons, meaning that you actually have to throw away a fair number of photons to employ adaptive optics. I'm a lot more interested in collecting as many photons as possible than I am about getting good image quality. So if I had an adaptive optics system, I wouldn't even use it because I wouldn't want to suffer the penalty of throwing the system.
Readout complete.
You mentioned it's $140,000 a night for the telescope you're on. What about the James Webb Telescope?
Oh my goodness, I wouldn't even hazard a guess. The entire mission cost of JW was, I don't even know what it ended up at. I think it was close to 10 billion or more dollars. So if you amortize that over it was supposed to have a 5-year mission, which was limited by the station keeping fuel that it has. But their launch was so good and just spot on that they ended up arriving at their orbit with a lot of extra fuel. So it wouldn't be inconceivable for JW to last 10 years. So if you amortize $10 billion over 10 years, it's $1 billion a year. It's roughly, what is that? Let's call it close to $1 million a day.
I think it's about 33.9 million.
There you go. So it's expensive.
Needless to say, you're not going to be using it anytime soon.
Oh, I actually have already used the James Webb Space Telescope.
Okay.
Yeah, so I've been involved in a handful of projects on James Webb. The
Wow.
one that I'm most involved in is about measuring the compositions of stars in the Andromeda galaxy, the M31 galaxy, our nearest neighbor large galaxy. James Webb's telescope observes mostly in the infrared part of the spectrum. And so we've been taking spectra in the infrared rather than in the visible. The light that you're looking at here with KCWI is all visible light. You can actually see it with your eye. But James Webb looks at light that has longer wavelength than your eyes can see. Principle, though, is the same. There's still absorption lines in the infrared, just like there are absorption lines in the optical. The star doesn't know that human beings can't see it in the infrared. So all the physics in the infrared is just the same as it is in the optical. I say optical, but that's astronomer jargon for visible light. We should really say visible, but we say optical.
So you can discover the same elements via optical as well as infrared?
That's correct. Yeah. For the most part, most of the elements that are represented in visible absorption lines are also represented in infrared absorption lines. There are a few exceptions, but for the most part, that is true. Generally, the heavier elements of the periodic table tend to be in bluer light, and that's simply a result of chemistry, where the electrons live, the valence electrons, and live in which shells, which electron energy level shells. We're in a bit of a lull in the activity right now, which is a good thing. Boring observing is good observing. If it gets exciting, it usually means something's going wrong. But right now we're just waiting for the exposures to finish. The longer we keep the shutter open, the more photons we can collect. And so we're just keeping that shutter open for about 5 minutes at a time. We keep the red shutter open for about 5 minutes, that's 300 seconds. You can see that number right here, exp time, exposure time. Whereas on the blue side, it's 1200 seconds, which is 20 minutes. And again, the reason that the blue side can have longer exposures than the red side is that the red side just gets too many cosmic rays. The longer you keep the exposure going, the more cosmic rays you collect. And so we compensate for that by just taking more exposures in the red, more but shorter exposures in the red.
Exposure complete.
Anybody have any questions about the Keck telescopes or the science that we're doing tonight?
Well, I will mention, Evan, that as a follow-up to what Scott was asking about the cost of
CCD readout complete.
the cost of a night on JWST, you mentioned some of your work on JWST, and I dropped a link to one of your papers, the right here in the chat there, in case you'd like to talk about that.
Okay, thank you, Jamika. Which one? Let's see. Oh yeah, that's exactly the one I was talking about. Thank you, Jamika. Yeah, so this is a paper that's led by my colleague David Nightover, who's at University of Montana, or sorry, Montana State University. If you can actually see on my screen, I've clicked on it. I'm going to scroll down and show you where in the Andromeda galaxy this field is. Zoom in here. So this here is the center of the Andromeda galaxy, and we pointed the James Webb Space Telescope at a field kind of way out in the outskirts of the disk of the Andromeda galaxy. Now the JWST pointing is actually much smaller than this red rectangle would lead you to believe. It's actually probably just like the corner of this letter B. It's a really, really small field. But I think that David put a spectrum. Here we go. So this is what a spectrum looks like as obtained through JWST. So JWST has spectrographs in it. It's actually different from Hubble in that regard. Hubble only has a couple of spectrographs. JWST is basically a spectrograph machine. Most of its instruments are spectrographs. So even though JWST has made beautiful, pretty pictures, the real money goes into the spectra that you get, not the pictures. And so we've got literally spectra of literally hundreds of stars, but this is just an example of two of them. One of them is in the foreground in the Milky Way, so it's in our own galaxy. Whenever we look at galaxies outside of our Milky Way, we have to look through the Milky Way, so it's inevitable that some of the stars we observe will be part of the Milky Way. And this is a spectrum of a star in M31 in Andromeda. M31 and Andromeda are different names for the same galaxy. And you can see a bunch of absorption lines dipping down. The way that we measure the composition of this star is we take the black spectrum, which is the observed spectrum, the one that JWST observed, and then we make a model of it. So we have a physics-based model of that spectrum. We change the amount of the elements in the spectrum until the model best matches the observed spectrum. So we're just basically matching the red to black, and we can change the parameters of the red spectrum until we have the right model. It's about as simple as that. Is turn the knobs until you get the right answer. And in this case, the right answer is shown here. So what you're looking at on the x-axis of these plots is the amount of iron in the stars. In general, over time, stars increase in iron abundance. That's because the galaxy becomes more and more enriched in elements as more and more supernovae explode. If you wait long enough, then some stars will explode and they will make heavy elements in the periodic table, including iron. And then the next generation of stars to form will incorporate those elements. They'll be more iron rich. And then some of those stars can explode and make even more iron. And the next generation of stars to form will be even more iron rich. So as you go from left to right, you're really looking at a sequence of time in the galaxy. The y-axis has a ratio of alpha to iron. Alpha is really just an alias for a group of elements in the periodic table. This group includes things like magnesium and silicon. The reason that they're grouped together is because they're all made in a similar type of event called a core collapse supernova. Those supernova happen very promptly early on in the universe, whereas iron tends to be delayed, comes out later in the universe. And when we look at stars in the Milky Way, we see a really strong separation of two different sequences. It's high alpha sequence and a low alpha sequence. But what we found in Andromeda is that the low alpha sequence is missing. And that tells us something about the formation of the stars in Andromeda. In particular, we believe that this low alpha sequence in the Milky Way was caused because the Milky Way was just sort of slowly plodding along at forming stars. We say it has a low level of star formation or an inactive star formation history. On the other hand, the high alpha sequence happens because you get a very sudden burst of star formation with not much lag in between one star forming from the next. It seems like M31 had this burst, but then it didn't have this continuous low-level star formation that the Milky Way seems to be dominated by. And the main conclusion is that the formation of Andromeda seems to be more violent, more quick and bursty, like a big flash and then nothing. A lot of sound and fury. Whereas the Milky Way had that burst, but then
CCD readout
persisted with this low level of just percolating star formation for a long time. So even though we believe that Andromeda and the Milky Way kind of look like each other, they're both large spiral galaxies. If you have this spectroscopy and you can measure the compositions of the stars, that kind of reveals stark differences in how quickly those stars formed. So we kind of got to the same endpoint, but through very different paths. There's a term for this kind of investigating the history of galaxies. It's called galactic archaeology. We are figuring out what the past of the galaxies is based on the evidence that's present today. So you imagine you go to an archaeological site, like you go to Egypt, you go to the Great Pyramids of Egypt, and you can see all of these artifacts. If you're an archaeologist like Indiana Jones, you can dig up artifacts and learn what that civilization was doing thousands of years ago. In the case of galaxies, if you just take a picture of the galaxy, it's not easy to know how the galaxy ended up looking like that. But with a spectrum, you can figure out what the stars are made of and make inferences about how the galaxy got to be that way. What path did it take to get there? What was its history? And so that is the technique of galactic archaeology. I consider myself an extragalactic archaeologist because I'm looking at the history, not of our galaxy, but of galaxies outside of it. So I call myself an extragalactic archaeologist. I'm going to check back in now on how KWI is doing. For those of you who like computers, the program that I'm using on my computer to do this observing in Hawaii is actually very simple. It's called VNC, Virtual Network Console. What that means is that I am just opening up the desktop on a computer in Hawaii. And so when I move my mouse, the mouse on that computer moves, or the cursor on that computer moves. And I'm just using all the programs on that computer. But the thing that's running on my computer is just basically a dummy terminal to that computer in Hawaii. So there's nothing fancy installed in my computer. There's no fancy software. All the fancy software, all these controls are being run from a computer in Hawaii. Know that there's some computer savvy people on the call, so I thought you might like to know this is just a VNC. It's actually 4 different VNCs to 4 different desktops.
The same thing I use at home.
There you go. I see Microsoft has remote desktop, very similar, exactly right. Yeah, that's exactly right. So I actually run Linux on my machine, so I just have a Linux version of remote desktop. It's called Tiger VNC. That's what remote observing consists of now. It's a bunch of VNC sessions like you see on my screen and a Zoom connection. And so my Zoom connection to the telescope is on my phone right now, so I could talk to you on my computer.
There might be a little knowledge involved too.
A lot of faking it. It's actually because of the pandemic that we're doing remote observing so often now. Previously, Keck required you to go into either go visit Hawaii, which isn't the end of the world, or to go to one of just a handful of certified remote observing sites. And Keck was so their policy was very, very conservative in the sense that they only wanted you to be able to use the remote observing with the Keck telescope if there was a backup internet connection. So imagine right now if my internet at my house failed, then fortunately I have my graduate students in different sites and their internet probably wouldn't fail. But if I lost my internet connection for some reason, and I was the only one observing, I was the only observer controlling the instrument, then I'd be wasting all of that time, that $140,000 a night. And so these dedicated remote observing sites at various universities around the world had backup phone lines. They actually literally had a battery of dial-up modems that would kick
Exposure.
in if the Ethernet line went down, if the T1 connection went down. But the pandemic kind of prevented that from happening because you couldn't go into the university to use those sites. And so they decided to open it up to people at home. They call it pajama mode. I'm not literally wearing pajamas, but you could get the idea. And even though the universities are open up now, the remote observing from home was so successful they decided to keep it, which I'm very grateful for because I'd much rather be at home in the middle of the night than in my office. It's also a really unsettling experience when your colleagues start coming into work at 8 in the morning and you still have to stay up until noon and then just like groggily try to leave. And people are wondering why you're leaving work at noon. It's because I haven't been to sleep yet.
I hope you slept during the day today.
No, I mean, I slept till about 9. I couldn't sleep anymore. And then I had to go to work and do my normal thing. I came home and I started observing. Thank you very much, Rosalie. It's all going very well, thanks to you. Bye-bye. That was our support astronomer saying good night. Well, temporarily good night. The support astronomers stick around for the first few hours of the night, and if everything's going well, they'll go to bed and then they'll be on call. So I have her phone numbers. I can wake her up if I need to. Hey, did y'all get Rosalie's phone number? Oh, Tony probably has it if we need it. Oh, it might be. Let me check. Yeah, she left it. Thank you, Gian. Yeah, she left herself. That's good. Yes. Oh, I'm showing you all my email. I shouldn't do that. Go back to the run.
I was just about to mention that.
Thank you. Oh, Eric asked, she's off mountain in Waimea. Yes, that is correct. So the support astronomer, her name is Rosalie McGurk. She is not on the summit of Mauna Kea. She's at the Keck headquarters, which is at a much more reasonable altitude. Keck doesn't like to put too many people on the summit because there's not very much oxygen there. It's at 14,000 feet and the air is very thin. And so you don't want to have too much, you want to risk having too many people up there in case one or more of them gets altitude sickness. And so most of the support staff works at a town called Waimea or Kamuela Highway. They're both the same town. There's just different names for it, Waimea or Kamuela. If you've ever been to the Big Island of Hawaii, it's sort of on the northern end of Mauna Kea. If you go from the airport to Waikoloa, you just go a little bit past it, and then you end up in Waimea. Waimea is at an altitude of about 4,000 feet, so it's perfectly nice altitude to be at. You're not going to be deprived of oxygen. But they're using the same VNC software that I am, so they are accessing computers on the summit of Mauna Kea. Oh, thank you, Eric. Eric, do you live in Kailua Kona? Oh, very good. You enjoy it.
Exposure complete.
I have an assistant observing with me. She's very experienced at observing herself. She's been through this many times. She knows how to operate now.
Complete.
This is Panda Bear. She's very sleepy. She's wondering why I'm bothering her at 2 a.m.
He just wants to be on your lap.
She definitely does. She definitely does. Oh, cool. That's a lot of energy, Eric. By the way, if y'all are interested, I have a research website. I'll put it in the chat and we can learn a little bit more about the research that I do. I can show you on my screen. So this is just a very brief introduction to some of the research that I do. In fact, you can see a picture of some of the people I've been talking to. That's Evan Nunez. Evan Nunez, he's the one who's observing the quasars now. This is Juyun. She's the one who's been making sure I don't screw up and make mistakes. Pranav Nalamwar is a PhD student at Notre Dame. He's also on the call. Roman Gerasimov, Lauren Henderson, Katie Kavasova. These people are all on the call right now. They're on the Zoom session, and they are also looking at the VNC screens that I'm looking at. I'll put this in the chat. Oops. I'll put that in chat to everyone. And if you click on research, I've written a little bit about the different aspects of the things that we do with the Keck telescopes. We can learn about what I mean when I say galactic archaeology, about chemical evolution, or how galaxies change their elements. You can learn about nucleosynthesis, or about how stars make the elements of the periodic table. And you can also learn about how we collect the data. So talk about which telescopes my group uses and which spectrographs in those telescopes. Eric, you asked about saturation and pixel bleed. That's a great question. Let's go back to the VNCs. So let's see if I can zoom in a little bit. Well, I don't really want to mess up what Evan's been looking at, so I won't zoom in. But you notice on the bottom left here, I'm looking at the red image from the red spectrograph. When I move my cursor around, you see the top right up here, there's a zoom in view of the image. So you can kind of see the individual pixels. I really should zoom in more, but I don't want to mess up what Evan's looking at. But each pixel in the detector is like a light bucket. It's actually an electron bucket. CCDs operate, the detector called the charge coupled device, a CCD, operates based on the principle of the photoelectric effect, which actually won Einstein one of his 2 Nobel Prizes. So Einstein discovered that photons interact with electrons, that if a photon, a particle of light, strikes an electron, it can actually make it jump up in energy level. It can cause electricity to flow in a piece of metal. So this particular piece of metal is a semiconductor, so the electrons can kind of move around, but not really. They can be confined to pixels, they can be confined to buckets. And so what happens is, as a photon hits the piece of silicon, it excites an electron to jump up into one of those buckets, jump up into one of those pixels. But just like a bucket that holds water, it can overflow. It can only hold so many pixels. And so, it can only hold so many electrons. Each pixel can only hold so many electrons. If you overfill that bucket, it's called saturation. And each of those buckets has a maximum number of electrons that it can hold. In the case of the red detector, that number is 65,000. If it exceeds 65,000 electrons, then the pixel saturates. And what happens is that charge, that electron, those electrons start to flow into the adjacent pixels. So this is called pixel bleed, which is the effect that Eric has mentioned. So if you overflow those buckets, it'll flow into the next bucket, the next bucket, the next bucket, and you'll start to see these long streaks of saturated bleeding pixels. It's kind of a gross term to call it, bleeding, but that's what it is. Bleeding electrons.
How often does that occur where you're bleeding electrons?
It doesn't happen too often in the middle of the night because we tend to be looking at faint things in the middle of the night. But on the margins of the night, in the twilight, that's when we do our calibrations. And our calibrations really bright stars. The really bright stars can sometimes saturate the pixels. So you more often see this in the calibration data, not so much the science data. It's not a big deal to have that pixel bleed. It kind of ruins the pixels that it happens to, but it doesn't really affect the whole image. And if you just take another image with a shorter exposure time, then that'll fix that problem. There's a setting on the detectors called gain, which is the number of electrons that you get per photon. Right now, that gain is 5. So every photon that's detected, we actually get 5 electrons coming out. But you can change that gain. And KCWI has 2 settings, a gain of 5 or 10. A gain of 10 makes it a little bit more sensitive, makes it a little, but a gain of 5 allows you to expose longer without saturating the detector. The stars that I'm observing are considered quite bright as KCWI goes. Some people who use KCWI that are observing galaxies that are 100 times fainter than the stars that I'm observing. In that case, they would want to turn up the gain as much as they can. But turning up the gain also turns up the noise on the detector as well. So you get sort of noisier spectrum. So I turn down the gain so that I can have extra headroom for not saturating the detector, and so I can get less noise. So I answered finally the question, turn down for what? And it's to turn down for getting less noise.
I am laughing on mute.
Eric, are you Eric, are you in the technology sector? You know about saturation and pixel bleed? Oh, very good. Oh, wow. Physics is my hobby too. I just happen to get paid for it. So I get a few nights a year on the Keck telescope, and that actually sustains most of my research. Well, pretty much every paper I've ever written, not every paper, like I've done some work with James Webb, but that's not the majority of what I do. The majority of my research is with the Keck telescopes, and I'd say 3/4 of the papers that I've been involved with have been on Keck data. But I only use the Keck telescopes a few nights a year. And so those few nights are so data rich that sustains my whole career. And so this is very, very high throughput. It's a lot of information coming at us right now. And these data cubes are so complex that it's going to take months to write the analysis software to make sense of it all. Each one of those stars has its own spectrum, which means I'm going to have to make a model of each one of those stars, meaning I have to know the composition. I have to make a model that responds to the composition of the stars, how much iron, magnesium, etc. And also things like the temperature of the star, because it also affects the shape of the spectrum and what the absorption lines look like. But then I also have to figure out where the stars are on the detector inside that data cube. And I'm going to do something called a forward model. I'm going to make a model of the entire data cube, meaning of all of the data that are coming out now. And that model is going to have something like 80 parameters. It's going to be a temperature, an iron abundance, magnesium abundance for each one of the dozens of stars in there. And even things like what is the size of the disk of the star that we're looking at. When I have all those parameters correct, my model is going to look pretty close to the data that we're getting is. It's never going to be exact, but it's going to look pretty close. So the
CTV
trick is
readout
to
complete.
change all the
CTV readout
parameters of the model
complete.
until it looks as close to the data as possible. And that's how I do the measurement. Changing those parameters is the measurement of the compositions of those stars.
Do you do your computing at on site with the Keck, or you transfer the data somewhere else and use it?
That's a good Yeah, that's a good question. I transfer all the data to a desktop computer in my office. It's a fairly powerful computer. It has 36 processors.
No.
The processors aren't particularly fast themselves, but there's 36 of them, so I can do some parallelization. If I wanted, Notre Dame has much more powerful computers with many more processors, but that's not needed for this kind of data. The software that takes this raw data and turns it into the data cube that Juyun is using, she's doing what's called the quick reduction, and that takes a few minutes. But to do it, to get the best signal as possible, it can take about an hour of just computer runtime.
So your observation this evening, how much raw data is it going to be? How much will you have to transfer to your desktop?
That's a good question. Let's look up how big each one of these. Let's look. I'm in the top left window right now. I'm going to look up how big each one of these files is. So each one of these images is only 9 megabytes. So it's kind of the same size as an image you might take on your cell phone. And so far, we've taken close to 100 images on each the red and the blue channels. By the end of the night, that might be 300 or 400. So 300 or 400 times 2 for red and blue times 9 megabytes. We're only talking a few gigabytes worth of data. Kind of amazing, right? That it sustains months of writing papers. Not to mention PhD theses. I mean, some of the students on this call might be writing a portion of their PhD thesis on this data. When I say this call, I mean the other Zoom that I'm also on, and they're talking in my ear. Well, that's a good question, Jamaica. So Jamaica in the chat has asked, how can we follow the progress of this research? That is a very good question. So I will be observing a very similar observing run plan on December 7th. And I think I've signed up for Out of the Scientist thing too. I'm not sure if I have it. If I haven't, I will. And you can check in with me then. You can see if I've made any progress on these data cubes. The answer, I probably won't. I'll probably wait for the data from December 7th before I reduce everything as an ensemble. And then I'm going to work with one student in particular to write the software to do that forward modeling that I was mentioning.
The readout
And then I will be posting the paper that we write probably next summer on the archive. So the paper that Jamaica has posted on the chat a little bit up was a paper on the preprint server, the archive, where we disseminate early results from our observations. And I'll be posting on the archive probably next summer about this data. My observing assistant is ferociously licking her own paws, so she shouldn't. Eric was a laser spectroscopy, a laser spectroscopist. How much longer until Fornax rises? Fornax will be rising about an hour from now. So we still have a ways to go on these. Oh, maybe half an hour from now. So we still have a little bit longer to go on these quasars.
So the other Evan, is he doing anything with the telescope at this point, or?
We are waiting for the exposures to keep exposing. So we're just collecting photons.
Oh, I see.
We're not touching the telescope. The telescope is just passively tracking the sky. So as the sky rotates, the telescope is tracking it to make sure that our image stays in the same spot on the detector.
You're waiting for both the blue and the red exposure. I see. Okay.
Yeah, you can see the exposure progress bars in the blue and the red. They're slowly creeping up towards 100%. Oh, if you look at this projection here on the blue side, this is a classic spectrum of a quasar. Remember how I mentioned that there's this emission line called Lyman alpha? That's this thing here. This is the Lyman alpha emission line, this big towering peak of emission of light. I also mentioned that the quasar itself has a bunch of absorption to the left side, or the lower wavelength side of Lyman alpha. So you see all this forest of absorption lines over here. Whereas on the right, those photons don't have enough energy to excite hydrogen. And so all these absorption lines here are different elements in the foreground of that quasar. So Scott earlier had asked, how do you know what's part of the quasar and what's part of the foreground galaxies? The stuff on the blue side, the lower wavelength side, is part of the quasar, and the stuff on the longer wavelength side is part of the foreground galaxies.
So are you able to pick up as many elements with the, especially in the lower wavelength side?
No, so the gas that Evan is looking at in the foreground of these quasars is a very different type of spectroscopy than the stars that I've been looking at. The stars that I've been looking at, you can observe half the elements of the periodic table because they all have absorption lines in the stars. The gas is a lot sparser, and so there's only 2 or 3 elements you can observe in the gas. So we won't be able to do nearly as much detail. So Evan is on the top left,
Exposure
poking
complete.
around trying to find those foreground galaxies. Right now his cursor is centered on the quasar itself, but he's also looking for the galaxies that might be just off of the quasar. So there's little specks of light all around the quasar that might be foreground galaxies, which is what Evan is interested in finding.
CCD readout complete.
So I think Evan's going to do one more exposure on this quasar and then move to a different quasar. Yeah, we still have half an hour before we move to Fornax. what you're looking at now is just Google Sheets, but it's my run plan for tonight. You can see that at 9:55 Hawaii, 11:55 Pacific, 2:55 Eastern. That's when we're going to be moving to the Fornax dwarf galaxy. But right now, in a few minutes, Evan is going to be moving to his next quasar. However, if I'm not mistaken, I think we're pretty
Exposure
much at the end of
complete.
our Shadow of the Scientist session.
What did you say you were interrupted by the voice in the back?
Oh, I said, if I'm not mistaken, I think we're approaching the end of our Shadow of the Scientist session.
That's right. We are, Evan. But before we do that, Eric has a question there.
Is there a way to determine the distribution of these various elements in the star's atmosphere versus within the body of the star? That's an excellent question. The answer is not really, not directly. The reason is that the star is opaque. We can see a little bit into the surface of the star, but not much.
Exposure
And
complete.
if you try to look deep into the layers of the star, you can't do it because the star is
Readout complete.
not transparent. So when we look at the spectrum of the star, we're really only looking at the very outer layer of that star. There are tricks you can do to like infer is stuff being dredged up from the bottom of the star, but in terms of the light we're actually seeing, it's just the outer layers.
CCD readout complete.
Are there any additional comments or questions before we wrap up our shadow session with Evan?
I'd like to say thank you very much. It was awesome. Learned a lot.
Thanks for coming, Scott.
Yes, thank you to everyone for joining us this evening. And thank you to Evan and your wonderful students and all of the amazing telescope support staff for making this possible. We certainly look forward to your December session, Evan. I will follow up with you on that one.
All right. Thank y'all. Have a great night. Thanks for staying up so late.
Aloha.
Aloha.